Section 5.2, Inverse Functions and Their Representations. Inverse operations. In mathematics, the concept of reversing a calculation and arriving at the original value is associated with an inverse. So here's a nice diagram to explain what's happening with an inverse function. So typically when we have our normal function f, we take inputs in our domain or our x values, we plug them into our function, and we get out y values, which we call our range. Your inverse function will do the opposite of this, so it will take values from your range, put them through the inverse function, and give you back the value from your domain. However, we always call our input our domain. So the domain of our inverse is the same as the range of our normal function. Similarly, we call our outputs our range. So the range of our inverse is the same as what our domain was for our normal function. We basically are undoing all of our work. If f and f inverse, again, this is the notation for f inverse. It's not the same as a negative exponent. So f inverse of x does not mean to put it in the denominator, like a -1. This is not what this is talking about. This is just notation meaning inverse. So if f and f inverse are inverses, then f of a will equal b, and f inverse of b will equal a. So again, whatever you put in as your input and get back as your output, your inverse will put the output as its input, and its output will be your original input, right? It undoes the work you were doing. So what we saw from this diagram was that the domain and the ranges are interchanged for inverse functions. Now, not every function has an inverse function, and here's an example of one. So for a function, each input will yield exactly one output. But notice for this function here, g of 2 is equal to 68. If g had an inverse, the inverse must take 68 and produce exactly one output. But notice when I have the number 68, I'm either going to have come from a 2 or from a 4. So your inverse function uses the range as its domain and the domain as its range. So if I were to put, I should use g. If I were to use g inverse of 68, well, here I would get 2 or 4, and that's a problem because if I'm a function, I should only get back one output for every input. So I should just get back 2, or I should just get back 4. So since I have two different answers for the same input, this is not a function, which means that my g of x does not have an inverse function. If you want to guarantee that you have an inverse function, your original function needs to be what we call a one-to-one function. So a function f is a one-to-one function if, for elements c and d in the domain of f, where c and d are not the same, this implies that f of c will be different from f of d. Or in other words, different inputs always result in different outputs. So we had a problem up here when we input 2 into our normal function g, we got back 68. But when I put in 4, which is a different input, I got back the same output as 2. And if it was a one-to-one function, it would give me back a different output. Exercise 1. Find the inverse function of f of x, given that f of x is the cube root of x minus 2. So here are the steps you take to calculate an inverse function. First, you want to rewrite your function with y and x. So change f of x into y. Then you want to switch your x and y's. So now I'm going to write x equals the cube root of y minus 2. And maybe this makes a little bit of sense, even though it might be the first time you're seeing it, because we talked about a few minutes ago that your inverse and your normal function interchange domain and range, or in other words, they kind of interchange their x and y values. So what you used to put in as an input and get back as an output, that output is now your input, and your input is now your output. So we switch our x and y's, and then you just want to solve for y. So if I want to get y out of this cube root, I need to cube both sides. So I'm left with x cubed equals y minus 2. And then I'm going to add 2 to the other side. And then I'm going to rewrite y as f inverse of x. And I'm going to rewrite the order just so that that comes first. So my inverse function is equal to x cubed plus 2. Inverse function. Let f be a one-to-one function. So the thing where if you put in a different input, you get back a different output. Then f inverse is the inverse function of f if f inverse of f of x, or the composition of f inverse and f, equals x for every x in the domain of f, and f of f inverse of x equals x for every x in the domain of f inverse. So basically you want to do both compositions, and each time you want to get back just x as your answer. So we're going to verify that the functions we just found in exercise 1 are actually inverses by doing that composition. So what we had for f of x was the cube root of x minus 2, and what we had for f inverse, or what we found, was x cubed plus 2. So let's start with f inverse of f of x. F of x is this cube root of x minus 2. So I'm going to write that inside. Now remember how composition works. I'm going to go into my f inverse function, and instead of having x, I'm going to write the cube root of x minus 2. So that's my new input. So notice it looks just like this function, but instead of x, I have this new input. And now we want to simplify this. So the cube root and the cube are going to go away, just leaving x minus 2. Then I have that plus 2 on the outside. Those are going to add to 0. And I do get back x, which is what I wanted, right? Our rule said we should get back x when we do this composition. Pause the video and do the opposite composition on your own. So do f of f inverse of x and see what you get. And again, if you do the composition in that direction, you should also get x as your answer. So notice f inverse is x cubed plus 2. I plugged that in for my x value into my f function. The plus 2 and the minus 2 went to 0, so I was just left with the cube root of x cubed. The cubes and the cube root go away, leaving just x. So this shows that our functions, the cube root of x minus 2 and x cubed plus 2, are inverses. The horizontal line test. If every horizontal line intersects the graph of a function f at most once, then f is a one-to-one function. All right, so we're already told that the graph is a function, but we're checking if it's a one-to-one function. So if you remember, we have another test that sounds similar to this that we use to test if something's a function, and it's called the vertical line test. Let's start by looking at x cubed, which we know is a function. The graph looks something like this. So originally when we talked about functions, we used something called the vertical line test, and we would put lines through our function, checking how many times the line touched, and if it touched more than once, then it wasn't a function. For example, when you draw a circle, it's going to cross more than once. So this passes the vertical line test, which proves that it's a function. So now that it's a function, we want to check if it's a one-to-one function, so we're going to use the horizontal line test. Kind of the same idea. So you're going to draw a horizontal line, and you just want to check if it's ever going to cross more than once. And for this, it's not. So what we see is that x cubed is a one-to-one function. Let's look at another function that we're pretty familiar with, the parabola, so x squared. So we know that looks like this. Again, if we are to do the vertical line test, this passes. There's never a point where we're going to cross more than once. So we know that this is a function. But when I do the horizontal line test, hopefully you can see right away that this will fail, right? There's a bunch of places, in fact, almost every place except for at this very bottom point, that a line's going to cross more than once. So x squared is a function, but x squared is not a one-to-one function. So what that means is x squared, the way it's written right now, is not going to have an inverse function. Exercise 3. Does f of x equals x plus 2 squared have an inverse function? If not, restrict the domain of f so that f inverse exists and find f inverse of x for the restricted domain. Well, we just showed a second ago that when you're a parabola, you do not pass the horizontal line test, right? And this is a parabola. This is degree 2 polynomial. So I have a feeling that this does not have an inverse function. But let's just look at the graph. So this is a parabola, our normal parabola, but shifted left by 2. So something like this. And again, this is going to fail the horizontal line test right away. So this is not a one-to-one function. But the problem asks, can you restrict your domain of your graph or just look at a part of your graph so that you could find an inverse function? And wouldn't this graph be okay if I erased half of it? Like if I got rid of that? Now it's going to pass the horizontal line test. So if I restrict my domain to just start at -2 and go on to infinity, this part of my graph is one-to-one. So for our restricted domain, let's use the interval from -2 to infinity, because the part of our graph that leaves now passes that horizontal line test. So now that we've restricted our domain, we can find the inverse function of f. So again, we're going to change f of x to be y. And then we need to switch our x and y values and solve for y. So take a second and pause the video and solve for y to find your inverse function. And then come back and check your work. All right, and our inverse function is the square root of x minus 2. Now maybe some of you got confused in this step right here when I took the square root, or when you were taking the square root, as to why I didn't put plus or minus. And I guess technically I should have, but just take a second and look at if I would have picked the negative version. So I'm just going back to this step right here. So if I would solve this equation at the very end, I would have had negative square root of x minus 2. So it's same thing here, but with that negative square root. Now, with our restricted domain, back on our original graph, our domain is from negative 2 to infinity, and our range is from 0 to infinity. So remember, for your inverse, your domain and range get flipped. So if this was my inverse function, I should be able to plug in values from my range and get back values in my domain. So let's say I plug in 1. Well, I get back negative 3. But negative 3 is not inside of my domain, which is the range of my inverse. But notice if I plug in 1 into the function that I did keep over here in blue, I get back negative 1, which is in my restricted domain. So for the part of the graph that I kept with this restricted domain, I should be picking the positive version of my square root. This one doesn't work for us. So that's why I kept the positive version. I just didn't really show my work there. I just wanted to talk about that. If you would have kept the other side of your graph, you would want the negative version of your square root, because then your restricted domain would have been from negative infinity up to negative 2. So it would be good to get back numbers like negative 3. But since we kept the right side of our graph, we want to keep this positive square root in our inverse function. Okay, so we calculated our proper inverse function for our restricted domain. Graphs of functions and their inverses. The graph of f inverse is a reflection of the graph of f across the line y equals x. So exercise 4, let f of x equal 2x minus 1, and we want to sketch the graph of f inverse. Well, let's start by just graphing 2x minus 1. We've done graphs of lines many times now, so this has a y-intercept at negative 1 and a slope of positive 2. All right, so here's our line f of x. And some of the points on this line are the point 2, 3, 1, 1, 0, negative 1, negative 1, negative 3, and so on. Now, the inverse will be a reflection about the line y equals x. So let's draw that line next. So that's just the line going through the origin with slope 1. So this is y equals x. And honestly, we don't even need to do the work of switching x and y to find the inverse. We can just graph it by switching x and y's in our coordinates. So if my function f has the point 2, 3, if I switch my x and y, my inverse should have the point 3, 2. This one is 1, 1, so when I switch them, I'm still going to be at 1, 1. The next point is 0, negative 1. So if I flip my x and y, I'm going to have the point negative 1, 0. I also have the point negative 1, negative 3. So if I switch x and y, I'm going to have the point negative 3, negative 1. And I get back this line. And this should be the graph of our line of f inverse. And notice that does look like a reflection about this red dotted line that I drew. Now you could check your work. You could solve this by switching x and y. and solving for y. So I get f inverse. I'm going to break this into two fractions. This is the same as 1/2 x plus 1/2. And let's check if this matches our green line. So I should have a y-intercept of 1/2, which I do. And if I go up 1 over 2, look at that, I still end up on this line that we drew.